Hello, Vanakkam, Namaskaram, Amit Vasudevan, research scientist at Scilab, Carnegie Mellon. I guess today I found out that the X200 tablet that I dearly own is officially a relic and not supported for presentation anymore. So I thank Ashish for lending me his laptop for my presentation. And I know you would all appreciate that for someone who's used to the ThinkPad micro joystick for a long time, I'm going to probably stumble on some controls here. So I would request you to please bear with that. I know all that stands between you and your lunch is me and my ranting and raving for the next 20 odd minutes, trying to summarize what we have been doing holed up for about 2.5 years. So without further ado, I will present überSpark, an innovative architecture that leverages verifiable object abstractions for automated compositional security analysis of a hypervisor. This is joint work with my colleagues Sagar Chaki at SEI CMU, Petros Maniatis at Google, Limin and Anupam Datta at ECE CMU. The modern hypervisor stack is by necessity extensible. Hypervisors are being extended with convenient functionality for various security services, attestation, debugging, application level integrity, trusted path, just to name a few. Extensible hypervisors, as a result, raise significant security concerns. Number of bugs go up with code size, number of extensions, update frequency of components, and complexity. Both VMMs and micro-hypervisors are prone to such bugs, as demonstrated by several practical attacks. This necessitates development of verified hypervisors that are accompanied by proofs of desirable security properties. Why aren't we already doing this then? Well, the cost of verification grows with the size of the code base, the number of different components, configuration of the various components, and the rate of revisions. Hence, verification needs to be compositional. Benefit of verification shrinks with the steep learning curve of verification-centric but developer-unfriendly programming models, lack of commodity hardware integration, and the magnitude of the runtime overhead. Hence, verification needs to be commodity compatible and performant. So why do this now? Formal C static analysis tools are very practical today. We use Formal-C, an industrial strength software analysis and verification framework. Formal-C provides several standard plugins for behavior specs, deductive verification, abstract interpretation, and so on and so forth, but also allows you to develop your own verification plugins via a very modular architecture. We use ComCert, a certified compiler, which is practical for moderate module sizes. This choice sits in squarely with our longer-term goal to ensure that verified properties carry over to the final binary. And last but not least, it's just way too cool to pass up the opportunity to roll up with big players while still carving a small niche for yourself. Let's take a motivating example, an extensible hypervisor. Hypervisor sets up MMU structures, sets up hypervisor and guest state structures, control registers, MSRs, communicates via the network. Imagine the hypervisor managing a multi-core guest on top of this and implementing various security extensions, which try to achieve various guest-specific and system-wide security properties. To add to all this, hypervisor and extensions are written in C and assembly. To construct and maintain a verified hypervisor of this sort, developers must not only build it and test it well, but also verify its code against a general set of safety properties, as well as functional invariants on hardware and software state. As you can imagine, this scenario poses several challenges. There you go, my first stumble. Challenge 1, code size versus verification. As code size increases, hardware deprivileging provides a very ready way to tackle compositionality in verification by compartmentalizing code with lower privileges. However, our initial experiments showed that doing this for a hypervisor inflicts significant performance degradation that gets worse as the number of modules and interactions between them increase. Also, as most of the hypervisor modules require some form of privileged access, this will require some expensive emulation with hardware deprivileging. Challenge 2, verification and continuous development. Hypervisor core and extension components evolve independently and continuously. Verification has to deal with this situation both from a cost perspective of re-verifying the system, as well as commodity compatibility where the development must not be hampered in any way or greatly. For example, verification of an extension like approved execution must not require coordination from another extension such as ROP detector or any other extension for that matter across revisions. Challenge 3, verification must support properties over shared system states. For example, extensions like hyperdep, which does data execution prevention, for example, and system call logging, which can log guest system calls. They both manipulate guest memory protections via the same guest page table structures. Challenge 4, verification must account for all possible configurations since extensions are optional. I could run only with hyperdep and the core hypervisor. I could run with both hyperdep and syscalllog. What is more, not all extensions come from the same developers or with the same pedigree. So you could have an unverified extension like ROP detector, but which is still taken into the build or into the integration as an acceptable risk. However, inclusion of ROPDET must not invalidate the properties of hyperdep, syscalllog, or for that matter, the remaining hypervisor core. Last but not least, the final challenge is that verification must go hand in hand with the programming paradigm. Hypervisors are written in C and assembly, the de facto system programming languages. However, often verification imposes high-level languages that are not developer-friendly and have a very steep learning curve. C and assembly can clobber stack, registers, CPU state. Verification must handle such scenarios while allowing meshing of C and assembly. However, current state-of-the-art verification tools largely lack support for assembly. Lastly, access to system hardware and multi-core enablement is commonplace in hypervisor. Verification needs to integrate such commodity hardware use and operations. However, current state-of-the-art verification tools mainly target sequential code and largely lack support for hardware integration. So the question is, how do we apply current state-of-the-art sequential source code verification tools which lack support for assembly and hardware integration, but still be tied, be into the hypervisor programming ecosystem? Enter the überSpark architecture, which addresses these challenges we've just described by leveraging a combination of commodity hardware mechanisms and software verification to achieve 3 goals: compositionality, commodity compatibility, and performance. With überSpark, developers prove behavior one component at a time and compose modules and behaviors cheaply, the notion of compositionality. They write code in C and assembly, and more importantly, they write behavior specifications in a C-like specification language, the notion of commodity compatibility. And finally, they execute with very little runtime performance overhead. Key to the power of überSpark is the enforcement of verifiable object abstractions that leverage commodity hardware mechanisms and software verification towards proving object security invariants. The solid lines designate hardware enforcement, dotted lines designate enforcement by software verification, and the dashed lines indicate a combination of hardware mechanisms and software verification. The basic building block is an überObject, which encapsulates specific system resources such as CPU privileged instructions, memory, and device interfaces, and provides an interface for accessing them with a well-defined behavior contract. An überObject can be sequential, can be concurrent. It can represent both verified and unverified hypervisor or extension components, the guest, and even system devices. A special group of Uber API überObjects, I'm sorry I'm missing my laser pointer, right at the bottom there, allow access to shared resources. So this enables state-of-the-art tools of automatic verification of sequential code to be soundly applied to verifying security invariants while still allowing multi-threaded high-performance applications. überSpark also defines a hypervisor blueprint. We call it an Uber blueprint. This basically provides a way to abstract hypervisor execution as an entire sequential program. The Uber blueprint, along with our high-level proofs and commodity hardware mechanisms, allow us to abstract this hypervisor running on a multi-core platform as a completely sequential program, allowing us to prove invariants and compose them. We'll look at these silent architectural components in more detail. Starting with the überObject. What is an überObject? What is it comprised of? An überObject contains C and assembly code operating on the private überObject data and system resources while interacting with platform hardware. The überObject also contains a contract that comprises a use manifest and formal behavior specifications of its own public interface written in a C-like language. The behavior specs guarantee that if a certain assumption is satisfied on the method of the überObject, then the property on the return values is guaranteed to hold. While our object abstraction is similar to existing microkernel and prior capability systems, überSpark is distinguished by privileged disaggregation. That is, we can now have multiple verified privileged überObjects that can be logically deprivileged. This results in us getting the sweet spot between verification and performance, as now we can execute with very high performance that would not be possible with something like hardware deprivileging, for example. The Sentinel is a special überObject that is present in any überSpark enabled hypervisor. The Sentinel ensures function call return semantics even when überObjects with different levels of privilege and trust invoke each other. It also acts as an object-to-object control flow enforcer. That is, object X can only call object Y and not vice versa. With überObjects verified not to write on each other's stack frames, Sentinel therefore enables sound application of state-of-the-art tools for automatic verification of sequential code towards verifying security invariants over sequential überObject invocations. Okay, we discussed überObjects. We spoke about the Sentinel, which allows us to have this sound abstraction of function calls, allowing us to express invariants over sequential überObject invocations. The next piece of the puzzle is how do we then introduce the sequence of überObject or sequential überObject invocations in a hypervisor with multiple extensions running a multi-core guest. Enter the Uber blueprint. The Uber blueprint can be thought of as a high-level control flow graph of überObjects. It basically achieves a serialized hypervisor execution by dividing hypervisor execution into 3 distinct phases. Phase 1 is called the startup phase. Again, I'm sorry for the graphic mix-up. It's because of the shift between the machines. Phase 1 is called the startup phase. The startup phase begins with a special überObject called the prime, the light green überObject at the top labeled with a P and at the bottom labeled with a P. The prime sets up initial state, which includes establishing operating stacks, setting up the CPU cores, and kickstarts sequential überObject interactions before launching a multi-core guest, the blue überObject with a G. The The sequential überObject invocations in this phase correspond to hypervisor-specific startup functionality, including extension-specific initializations. The dotted arrows indicate sequential execution. The solid arrows indicate concurrent execution. The circle at the start of the arrows indicate executions initiated primarily by the hardware. Phase 2 is called the intercept phase. Here, a special überObject called the iHub, the light green object with an eye, gets control and sets up sequential überObject interactions upon any triggered guest event. iHub eventually resumes the guest after the event has been handled. The sequential überObject invocations in this phase correspond to hypervisor and extension-specific event handling. For example, CPU ID emulation, data execution prevention, system call logging, etc. The final phase, phase 3, is called the exception phase. Here, a special überObject called the eHub or the exception hub, the light green object with an E there, gets control and is responsible for handling faults and exceptions within the hypervisor. For example, page faults or NMI watchdog capabilities, etc. The Uber blueprint, along with our high-level proofs, enable us to abstract this hypervisor into a non-deterministic sequential program. This in turn allows us to prove invariant properties of individual überObjects and compose them. Alrighty, we've established function called semantics. We know how to prove invariants over sequential überObject invocations. We have shown via the Uber blueprint how we can take this hypervisor that's executing on a multi-core hardware and convert it into a sequence of sequential überObjects. So we can now use state-of-the-art C static analysis tools to start verifying this sequential program that we have, correct? Well, not quite yet. Remember that piece of assembly and hardware interaction that the current state-of-the-art tools don't really support? Enter the last piece of the puzzle. We call it CASM and the überSpark hardware model. Hardware interactions in überSpark is carried out using assembly. Assembly language for a verified überObject is written using CASM, a dialect of C in which assembly instructions are encoded within regular C functions. We call them CASM functions. CASM can be thought of as a very close but more principled cousin of the inline assembly that most system developers are used to. Every CASM function has instructions encoded via C-like pseudo-instruction calls. We call them CASM instructions. In this example, write CR3 is a CASM function which writes to the control register CR3. And you can see that the instructions basically go ahead and move a 32-bit value into the CR3 register, which in this case happens to be the page table base register, which is responsible for governing the page protections. Each CASM instruction pseudo function is defined in the überSpark hardware model, and that bridges the shift between the reference C semantics and the hardware instructions and operations. And the hardware instructions and operations, including access to CPU registers, I/O regions, etc. During verification, each CASM instruction is replaced by its corresponding C source code from the hardware model, and the resulting C-only program is now verified for required properties. During compilations, all C functions are processed by ComCert, whereas the CASM functions are generated and dumped in as assembly language instructions. So far we have seen how we have abstracted and hypervisor as collection of überObjects. We can now verify invariants on the sequential überObjects and hardware state via automated verification tools that are targeted at sequential C source code verification. Let us now look into how developers code and prove behaviors of a sequential überObject. In this example, the überObject is having an interface to set up memory page tables. überObjects are written in C99 and CASM, as we've described previously. Behavior specifications are written in a language called the ANSI C specification language, or ACSL, which basically provides the requires, assigns, ensures triplet, which allows us to define function behavior. In this case, it is saying that this particular page table function sets up a 4 GB address map with appropriate page protections for ranges. Finally, this whole triple is proven automatically via pharmacy and its deductive verification plugins and an ensemble of SMT solvers. All right. How do we handle Uber objects that access shared resources now? How do we ensure that they don't break each other's invariants established on resource state? Up until now, we've been handling composition of invariants over sequential Uber object invocation. What about this sort of parallel composition where multiple Uber objects access a shared resource? überSpark implements Uber object resource interface confinement. Basically, you wrap around a reference monitor around a shared resource. Resources can be MMUs or control registers or other system-specific data. A special group of Uber API Uber objects encapsulate those shared resources over which systems properties are established. Client objects manifest on how they will use this shared resource, and this is verified on the client via assertions. And during integration, the use manifests are combined into one formula with the SMT solvers checking for composability. Remember, the composability checks are hypervisor implementation specific, and a more general composability framework is an interesting direction for future work. So let's summarize Uber objects or verifiable objects. Developers can code in C99, CASM, and ACSL, write behavior specifications in a very C-like sort of environment with behavior restrictions. They can prove object invariants one at a time and compose them. Invariants can include basic memory safety, control flow integrity, and other properties that can be formulated as invariants. The überSpark architecture ensures invariant composition. The first mind blow, you only now need to worry about object behavior, not implementation anymore. Second mind blow, a compositionally verifiable C plus assembly system without hardware deprivileging. We applied überSpark to XMHF, an open source micro-hypervisor for the x86 hardware virtualized platform. Originally, XMHF consists of a core hypervisor and a single extension called a HypApp. It runs Ubuntu 12.04 with 32-bit multi-core kernel on Intel VT and AMD. There have been various HypApps that have been developed on XMHF so far, including tracing, attestation, application level integrity, and trusted path, just to name a few. We ended up with Uber XMHF, which supports not a single extension, but multiple extensions. It runs the same Ubuntu 12.04 32-bit multi-core kernel on Intel hardware virtualized platforms. Our implementation consists of 11 Uber objects, totaling about 7,000 lines of code, including both the prime and the sentinel. And it took us about 3 person-months to refactor the original XMHF codebase to the Uber XMHF codebase and the überSpark architecture. Let us now proceed to discuss our verification results. The verification tool TCB comprises of pharmacy, the überSpark plugins, the SMT solvers that we use as the backend, and the hardware model. This TCB compares favorably with other existing verification approaches. We were able to verify security invariants in both the core hypervisor and extensions. Invariants included basic memory safety and control flow integrity, and other hypervisor and extension specific invariants such as no direct writes to hypervisor memory by the guest, data execution prevention, guest syscalls being logged to the network, etc. The 11 Uber objects had a total of 5,544 lines of ACSL annotations that we had to write to get these security invariants in place. The annotation to code ratio was 0.2:1 to 1.6:1, with the higher annotation to code ratio for Uber objects that needed to have some sort of functional correctness to support the security invariants. Uber object verification times ranged from 48 seconds to 23 minutes, with a cumulative time of less than an hour. The 23 minutes that I'm speaking of here corresponds to the prime, which in our experience can be further decomposed and into further Uber objects, and therefore you can reduce the time further. This whole effort of writing these annotations and coming up with these security invariants took about 9 person-months for a developer who was not familiar to ACSL. So let's look at some performance benchmarks. All Uber objects were compiled with full compiler optimizations turned on. The sentinel call overhead for verified to verified Uber object transitions is just 2 times that of a regular null function call. I guess we are running out of time, but what I want to sort of emphasize here is if you look at the verified to unverified transitions, you can see that it's an order of magnitude larger. Hardware deprivileging contributes upwards of 66% overhead. So the verified to verified transition gives us that edge of performance. We also compared Uber XMHF to vanilla XMHF. The verified hypapps imposed only a 2% average overhead. Unverified hypapps, obviously because of the hardware deprivileging, register saving, and parameter marshalling, incurred 10% average overhead. But the I/O and the normal guest performance remained unaffected. So what do we have here? We can prove behavior one object at a time, can compose models and behaviors cheaply, goals of compositionality. We can write system code in basically C and assembly and behavior specs in a C-like specification language. You can integrate hardware accesses and states into verification, the goal of commodity compatibility. And finally, we can execute with good runtime performance. What don't we have yet? It's not exactly C99 and assembly. You can't have any cowboy-style control flow craziness, indirect jump instructions, go to, and so on, which I think is probably good for secure programming in any way, and no C++. Our high-level proofs depend on ComCert's specification of the C memory and register semantics and CASM's adherence to those semantics. These are currently discharged as invariants on the source code and our hardware model. Future work involves cleanly extending the bisimulation proof of ComCert to encompass this hardware state and assembly code, and also demonstrating the semantic synergy between Frama-C, ComCert, and CASM so that we can translate all these proven properties right to the binary. Future work also involves proving refinement between the hardware model and the assembly language instructions that are generated. Again, this could be done via bisimulation, for example. Our focus on this work is on security invariants and functional properties to support those security invariants. However, we are optimistic that properties such as liveness properties and full functional correctness are achievable goals in the future. We are focused on a sequential serialized model for this hypervisor work that we've done. And we've been able to prove and generate a practical system with good runtime performance. However, we do realize the importance of relaxing the serialized execution model, going with full-blown concurrent verification, especially for high-performance computing environment. We are planning to use the source-level multi-threaded verification framework upcoming in Frama-C for such purposes in the future. And last but not least, our goal is to apply überSpark to a more broadly applicable set of domains. To build compositionally verifiable systems. So we are looking into other hypervisors like Zen and KVM and how we can translate them into the überSpark architecture, BIOSes, device firmware, operating system kernel and drivers, user space apps, and even browser extensions. überSpark is open source software. It's available at überspark.org. I'm pleased to announce the first academic prototype release. I'm codenaming it Cliff Jumper. This is a moving target with many more features and updates scheduled for the upcoming months and years, so please stay tuned to überspark.org. Comments, suggestions, criticism, and contributions are all welcome. I will now take any questions you may have.
Let's thank him. And, since we're running over time,